I just went through reports and I realized that reports are meeting the minimums requested, like the ERD was explained. Also, the part related to queries was completed. So almost all of the basically reports included all those parts, but the quality of some of the reports are very, it looks like some people did for the last minute, just some query, some very, very simple query, If your query is just involving one or two tables, it means that you haven't worked on your queries at all. So I would like to, and also for the introduction part, when you are explaining your problem, you have to draw some future work for that. You have to show some vision. Okay, so for example, you are doing hospital management system, okay, and you just chose 10 entities and that's it, and you cannot tell anything how this is integrated, how this system can be integrated to other systems. What is the feature that you are designing? What is the, if you cannot explain it, it looks like you got it from somewhere and you brought it just to the class for the sake of project. So this is, I would like to ask you to just put more time on, when you have a task. So your second project is completely easy, and you just need to write some lines of code of Java and fix the problem. But for the second part of this project, for the second phase, you have to involve yourself to something interesting. I would like to ask you to have three different branches. One is dividing, one group can choose either design a GUI for this database, using Java and including JDBC. The other direction could be running some benchmarks and check. And the other branches and direction could be distributing the tables and make the system distributed. That's I would like to give three choices for you, but here with this quality of some of the quality of the works are very, I'm telling that if you are doing, if you are writing just one paragraph of introduction, you cannot imagine how your system can be developed in future. It means that you haven't thought extendable, you know what I'm saying? And I also ask people to go and check other systems, when you are developing it. For example, if I get hired in a company and I was asked to develop a system for the HR, the first thing I will do is not just going to people and I'm doing some conversation, getting some information and then design here. I'll go on the web, check for other systems, and I'll go for on the edge technologies, like for example, different algorithms, how current Turing the database can support your system. So if one way is yes, when you are getting a task, just doing it for the sake of finishing the task. The other way is, dedicate yourself to the task and show your compassion to the task. So. We started database tuning. We talked about different tuning levels, right? We talked about normalization and denormalization. We talked about, did we finish redesigning database?
No.
Okay. So the other part is redesigning database, okay? So many people practice on AdventureWorks database, they realize that there are some one-to-one relationship between some of the tables, okay? continue on our database tuning topic. So we talked about denormalization now. Let's talk about redesigning tables. So what was the main topic? What was the main task when you designed the database? What was your main task? What was the goal of designing a database? What did you do at the end? What was the last task you did for the first phase of the project? You designed the tables, right? You mapped the entities and relationships to tables, and you realize that what kind of table you have to have in order to implement this database, okay? So sometimes based on the performance and based on frequently queries submitted to your database, you may need to redesign the database as you need to partition tables, partition vertically or horizontally. So a table could be a bottleneck for query processing if it is heavily used and it's used for updates and it is using OLTP systems, then there will be a lot of locks on the table, and if the lock level is even on the record level, then the table could be a bottleneck. So, and also if the index of the table is very deep, the table is getting larger and larger, and definitely the level of the table, the index of the table will be very deep. Or the size of the records are very large, okay? And it causes that the table grows very fast, and also the table gets very large. So in this case, the first solution coming to our mind is partitioning the table. So there are two types of partitioning possible. One is horizontal partitioning. What is horizontal partitioning? What is horizontal partitioning? Suppose that you have, where was this thing over here? Suppose that you have a table of set of A of records, okay? And A is including A1, A2, and A3, okay? So for horizontal partitioning means that I split the table A to three tables, A1, A2, and A3. So from now on, instead of one table, I will have three tables, okay? So basically what we are doing is we are distributing accesses to disjoint sets of records, okay? So we are partitioning the table into smaller tables. This partitioning can be based on the semantics of the tables. For example, if you have a data and the data is explaining some set of patients, and the patients are divided based, and the patients has this state as one of their properties, you can geographically, by the semantic, distribute and divide and partition the table, right? Or organizationally, for example, if you have a table of employees and you know that whenever you are submitting a query, employees of one department is just involved, then you can split the table based on departments or based on active and inactive. For example, when a person is graduated, then the record is not frequently used in the queries, then you can move the record to another table. Basically, this is also a technique of partitioning. So what are the advantages? What are the advantages? First of all, the lot contention will be removed, because instead of one table, big table, you will have a lot of small tables, okay? And then when you are accessing and when you are doing an update, you are going based on the semantics of the records you are updating, or based on the semantics of the records, based on the information in the record that you are trying to insert or delete, you refer to a particular table, and the rest of the tables will not be touched. Then you will not put any lock on the rest of the records, and they will be accessible. So the lock contention will be less. Indexes getting smaller, then the levels of indexes will be decreased. Also, uh, basically, rows are, no matter rows are big or enough, the size of the table will be smaller and they can concentrate in few pages. Then you will have less I/O. So, what are the disadvantages? What are the disadvantages? What are the disadvantages of this? It adds complexity. It makes it complex.
We have to use so many joins.
Right. You have to use not joins, but many things like functions or anything like that is looking for overall tables. It will be changed. And also, it will be difficult for queries that are involving all of the records, not just specifically. For example, if you have a database of patients and you divided tables based on the state of the patient, and now you are looking for Mr. Smith, okay, and you don't know in which state he lives, then you have to go to all of the tables and look for Mr. Smith, right? So sometimes it's difficult for handle all of the queries. So let me give you a very brief example. Okay, so here in the Adventure Works database, so let's see what kind of big table we have. Okay, suppose that here in the Adventure database, I split the table employee to two tables. Employee married, employee single. Okay? Now, you're supposed to write a function, okay, getting a specification of a person, okay, including name and his marital status, and return the business entity ID. No, there is no name over here, hold on. Including the specification of a person is business entity ID and marital status, and you need to return the gender. So write this function now on your database. Open your computers and write this function. We talked about functions, right? So do you have a computer? No, just show it as a computer. You can come over, you can join your friends over there, and you can work on your. Okay, who is done? Nobody? So now suppose that you can see over here I have two tables. Employee married and employee single, okay? So I want to write a function that scalar function, okay? New scalar function. So let's say its name should be project. Okay. What is the first parameter? What is the first parameter?
Business entity ID.
Business entity ID. What is the type of business entity ID? Integer, is it?
Integer ID.
Okay, so what should I put over here?
Professor, marital status will be named as it. It's supposed to be a character or something.
Nice. Oh, it could be. I got that 0 on 1. It's like
Okay.
it should be character also. Just made it easier for me. So okay, what is next? Declare TMP as. The TMP as. What was? If if marital equals to, for example, 0, we assume that it's single, then TMP will be equal to select Okay, so you have to write the rest as a select query, and you have to write two select queries for this condition, begin and end, and then you have to write the else part, and then begin and end, and finally you have to return temp, right? So you have to write two different queries. So you will see that the complexity is increasing. So I'm not gonna write all the queries over here. So it's just a simple select query. So I will post this as a homework to Canvas to finish this classwork. So the complexity of the horizontal partitioning is increasing the complexity. The other way is vertical vertical partitioning. So in vertical partitioning, we are splitting columns into subsets that are, and we are replicating the key, and the key is referring to the partitioning, and to in each table is repeated. So this is useful when queries are usually working with different subsets of columns. So, for example, in the employee table, you can, for example, you can divide columns in order to the columns related to compensation, and columns divided into job, and then these tables can be partitioned vertically. There is an example over here in the in the adventure work database. Is there anyone can show me where we have vertical partitioning? People who studied this database properly and well, they can show me where this partitioning happened. Where? So you can see over here, one. Where is that partitioning? Where do you see that the key is replicated? Is this the key for this table, right? Business entity ID. This is also the key for this table, password. The key is replicated, right? It means that this can be in the same table, right? But we partition the table because we do not touch password a lot, or for security reason. Okay? So this is an example of partitioning, isn't it? You have this passport hash, passport salt, and modified it on all of this inside of this personal passport. Okay? Another, let me see, Jason. No, Jason is not. Okay, now, I mean, we had a lot of partitioning over here in the sales part and other places. So, but at least you can see one partitioning. So This is an example of vertical partitioning. So the other way of increasing the basically performance of the data DBMS and enhancing the performances using extents and storage structures. Basically, what is an extent? What is an extent? Suppose that you want to define a file for a table, okay? So you want to put the table on the disk. So initially the table has 10,000 records, okay? So you put 10,000 records on the disk, but in case you guess that the table is growing, and in 2 months you will have 20,000, you will keep a file of size 20,000 for this table. Why? Because when you reserve a file of size of 20,000, it means that if a table is growing, all the pages will be consecutively added. So then the sequence of the pages will not be changed, and the I/O will be very efficient. So basically, allocating a table, an extent for a table, keeps the pages all together. But if we do not, let me give you an example. Suppose that you have this create table instruction. You created the table and table has 10,000 records. Okay. So suppose that you initially get this much of a space. So you initially get this much of a space, okay? You add 10,000 records to the file, and then you close the file over here, okay? In the second case situation, you have 10,000 records, but you get a file of 20,000 on the disk, and you put your 10,000 records over here. This space will be empty, okay? So when you have this extent on the table and you allocate more size, then if you add any record on this, so first of all, when you allocate this much of a space, then usually this space will be all together. All the pages will be consecutive to each other, okay? So when you add any record to this, then the record will be added over here, and when it is growing, then the pages added to the file will be exactly after the current pages, and the sequence of the sort and order of the pages will not be changed, and you will have more efficient I/O. But in the other case, when you add another record, okay, you want to add more records, then the DBMS gets some space from the operating system, but operating system not necessarily gives a space after this file. So maybe the pages, the data pages on the disk will be in another place. So these are added pages. Then when you are processing queries, the head of the disk should be changed a lot, and then it will be less performant, less efficient. Is that clear to everyone? So keeping extent means that you predict some sort of growth to your data, and you allocate higher and more space when you are creating tables. So the other factor to tune a database is using a storage, tuning the storage structure. So we talked about heap and indexes, okay? So what was a heap? Heap was an unsorted file. What happened is, when you were using heap, you were just adding records at the end of the file. So this kind of tables can be useful in some places, because when you always need to retrieve all of the records, and you are not doing search specifically on a specific key, then it doesn't matter you have index or not, it will go through all of the records. Then adding an index will be another overhead. So heap is good sometimes. Sometimes you can have integrated tables and index in the same file, okay? So for example, suppose that you have a B plus 3 or hash, and B plus 3 or hash is in the same file. So if the B plus 3 is in the same file, what happens? What was the feature of this B plus 3? What was the fill factor? Why didn't you study, why didn't you forget everything? You're not supposed, are you supposed to implement this B plus 3? At least, I heard that on weekend you went through. What was the what was the fill factor? What was the feature of B plus 3? Every node was not completely full, right? We always kept some free space to at least half of the, always 60% of the nodes are full, but the rest is empty in order to facilitate insertion to the index, right? So fill factor is in this case 60%. 60% of the table is full. We showed that in, for example, in SQL Server. So we showed that in SQL Server also we can adjust this fill factor based on your requirements. So when you have this fill factor, if you put the index inside of the same file, then since the index is not always full, then the index will be, you will waste a lot of space, and there will be empty spaces in your file. So you're wasting a lot of space. The file will be sparse, and in this case, the I/O will be inefficient. Why? Because when you have free space, wasting space, then you either have a larger number of pages, which is not necessary. So the other type of the structure very useful is sorted rows in a file. It means that we are sorting the file together with an index, which is cluster, because if the index is based on the item we are based on the activity we are sorting, then the index will be clustered, right? And we store index separately. If you store index separately, the story of empty spaces will be another file. So your file, your data file will not be sparse. Okay? So this is another important structure. We will see how it works. So basically, if you do not specify the primary key, but usually the database, DBMS, takes the or unique constraint, then the database will create the table as a heap file, okay, by default, because it doesn't want to bother himself. To add index structures, right? So in this case, you will not have any useful index on select, update, and delete queries. So you will have a lot of IO, excessive IO, and the what is the other problem? Suppose that you want to run a transaction, and the transaction wants to change some record. So the atomicity of transaction forces you to lock the part that you want to change. Okay, when you want to all of you have this example of, suppose that you have this transaction, transfer money from account 1 to account 2 amount, okay? So this transaction should be begin, okay, one update, account 1, should be, this is a pseudocode, where account 1, and then the other update should be, this is the amount, right? The second amount plus amount, and then where the account is account 2. So this is N. Suppose that you have this transaction, okay? So in order to make the database, to keep the database integrity, what you are doing is when you start the transaction, you put a lock on the area you want to change, okay? So you put a lock on this account. Because why? Because when you read the amount of the account, it was $10,000. You assume that it's $10,000. You're decreasing $10,000 to $500. At the same time, if another transaction interferes and changes the amount from $10,000 to 0, then you write $500 into account while it was supposed to be at least minus $500. Why? Because you don't know when you are calculate this amount, new number for amount, you don't know the other transaction changed it. So in order to make the transactions, in order to make the database integrity correct, you have to put a lock, right? So this is lock. So, but where do you put the lock? Where do you put lock? If you know which record exactly it is, then you put lock with that. But when you are working with heap, when you start your transaction, you don't know where the record is. So what you are doing is you are going through. So the scope of putting lock will be the whole table. It will be very, very inefficient. It means that at the same time, you cannot run two transactions at the same time. So and also when you are inserting rows at the end, it means that you are changing the last page, okay? When you want to write on the last page, nobody should write at the same time. Why? Because it may, for example, if you want to write at the last page and you realize that the last record is number 100, you want to put your record on number 101, the other transaction interferes. It also sees that the empty space is 101. He wrote his record, it's not. Then you are writing it on that and you are overriding it. So it's not good. So you have to put a lock over there also. So putting a lock, it means that when you are adding locks over locks, then it means that this is also contention and inefficient. So we talked about indexes. First of all, indexes were very useful. That's why we are creating it. So the indexes has had several advantages. It avoids table scan. It enforces uniqueness. What does it mean? What does it mean?
Record as unique index.
So if you want to make sure that no student has no pair of students have the same student ID, what you are doing, what you are supposed to do. Suppose that I have this school, I want to register the students. I want to make sure that I'm not giving same number, student number to two people. So yes, primary, you put this constraint that this should be unique. Enforcing the constraint that this is unique means that you have to have a device, tool, that go to the table and check before inserting. if that person is existing or if that student ID has been assigned to someone or not. In order to check it, you have to search. So in order to enforce the uniqueness, you have to have an index to search. So basically indexes are created automatically when you have primary key or you have unique constraints. We can have only one clustered index at the same time. Generally, clustered indexes are created on primary key. If the table does not have any primary key, so by default it doesn't have any clustered index. So you can input any clustered index on the table as you want. Let's see, the report is going on. Yes. Okay, so now let's consider different types of indexes and different structures of indexes. Suppose that you have a clustered index implemented as a sparse tree on the sorted rows. What does it mean? It means that we have a file, and on top of the file, I can show you this. We have a file. In the file we have records, and on top of the file we have a tree which has some places empty inside, okay, which is wasting some spaces. So So this is avoiding a scanning table for many SQL queries. It supports range queries. Why? Why does it support range queries? Oh, this is very. We talked about these indexes. I guess it was not 3 weeks ago. You forgot. You have to refresh. I'm a forgetful person, but when I need something, I have to repeat it to myself. Because one feature of the B+3 was supporting range queries. Okay, you start from scanning from the root, traverse the tree, and you get to some place that you can start. And since the rows and the leaves are sorted, then you can start scanning to the leaves and check the range, right? So, in this case, we are sparsing the data page because we want to keep the rows sorted. So, suppose that another important structure is integrated storage structure for hash. So suppose that you have a file. Suppose that you have a file and you have some rows here. On top of the file, you have a set of buckets, and the buckets, okay, and you have a hash function over here, and the hash function points to the buckets, and the buckets are pointing to the rows here, showing that where the rows are located. So this is another structure we talked about. This hash indexes does not support. Hash index does not support range queries. Why? Because we do not have any sort on that. Okay. Okay. So suppose that another important structure. we have a clustered index, okay? We have a dense clustered index, P clustering, okay? The index is stored in a separated file, stored separated. So we have a dense index, maybe full, because reorganizing the tree is not very difficult. And it's clustered, it means that the sort of these leaves are same as the sort of the file, right? And it is stored separately. It means that this is a file, this is another file. So, and basically, as I told, this file should be sorted, and this sorted leaves are pointing to a sorted file. So, again, this type of indexes are avoiding many data page splits. Why? Unlike the previous structure, in the previous structure, this tree was sparse. Also, keeping the rows sorted, make them sparse, okay? Because you need space, keep a space for adding future added sort.
40% space.
The 40% of the space will be empty. But here, the file is sorted, dense, no space is wasted. You have a separated file of index, which is not wasting a lot of space. So it's avoiding wasting the space for you. It also supports search queries. Why? B+3.
Yes.
B+3 is always good. Suppose that now this was clustered index over sorted file. Clustered, same sort. This is sorted file, clustered index, and this dense clustered index over sorted file. Another type of B+3, another type of index is dense unclustered index. So it means that the file is not sorted. You can see that the rows are randomly organized. They are not organized in the same way. So usually these type of indexes are hash indexes. It can be cluster index, but let's talk about hash indexes at this case. So we have buckets. We go to the buckets using a hash function. You remember that, right? Hash function sends us to a bucket, and from the bucket we get to the address of the row, and we are going to retrieve the row. Okay. So usually these indexes are created when we have unique constraint. Why? We talk about uniqueness.
Hash index.
When you want to check in uniqueness, what do? Do we run a search query, or we are running a equality search? Sorry, do we run a range query, or we are running just an equality search? Equality, just because we want to just find the row and make sure that it's not existing anymore. It's not existing right currently. Okay, so and hash indexes are good for equality search, and it's better for equality search for why? Better than B+3? Because in B+3 you have to traverse the tree. You have to go 1, 2, 3. But in hash index, one file, one number, go to the bucket and find it. So faster, very fast. So in this case, since we don't have we are not supposed to sort the file based on the search key. We can have any number of indexes. Basically, unclustered index can be on anything, and you can have a lot of unclustered indexes. So the search mechanism is similar to clustered index, but it's less efficient. Why?
No sorted.
It's not sorted. So when we want to find the record, find the range, for example. So we go through here, okay, then we find the row, and then the next row could be, sorry, let's not talk about the range queries, just let's talk about equality search.
Range queries work in these also?
What?
Range queries are applicable for
If it is unclustered, the range queries cannot be used with hash function at all. So, because first of all, you cannot use hash index on range query at all, because you don't know what is the next key, and you cannot go and use the index to find the next one. Because first of all, if it is unclustered, when you find one, the first boundary of the search, then you cannot go and scan the rest. You have to go and see all of the index where the query is matching, where clause matches. But even for B+3 also it's not good. Why? Because when you find one record, then in the B+3 index you go through leaves, right? But still you have to jump a lot in the main file from one place to another place. When you're jumping, it means that you loaded the page file, you read just one record of it, you are jumping, right? Then you don't need the rest, waste it. Leave it and go to another page. So this jumping means that you have a lot of I/O. So it's much less efficient than clustered index. Okay, so we will talk about index covering. So, what is an index covering? I'll talk about it later, but index covering is in general, keep in your mind that index covering means that you have some index, and the index is useful for your specific search, and it covers some part of your search, and it facilitates your search. Okay, if you have a query, either search is done for update or remove, delete, or anything like that. Index covering, if you have an index, it can cover some part of your search and facilitate it. It means that index is covering some part. So supporting index covering means that sometimes it can be useful. Okay, but it has overhead. Why? Why it adds overhead? First of all, you always have to keep updated index. When you are inserting or deleting anything to your database, you have to go and change your index. When you are updating, you have to change the index. Okay. Also, this is the, and when you are not using it, then it adds some overhead. So you can all of the DBMSs have these commands to create indexes separately. So specifically, if you do not have primary key on the table, currently on the table, and you create clustered index, the table will be reorganized and the table will be resorted. So you can try it at home. Create a random file in Excel, export it to a very big file, export it to 2 tables in the SQL server, both of them without any primary key, and try to put a clustered index on it. If you put a clustered index on it, it takes a long time to create the index because it sorts the file. You see, if you have this disks, you see the sound of this doing it. Okay, but if you are creating an unclustered index, since the sort is not happening, you just read the records, and the database is just creating the index. Okay, suppose that you have this database, this schema, and I will, on this schema, I will solve some problems. I will show you some problems about the tuning the database and see how we can tune a database. Suppose that you have a database, a small database with 4 tables: student, professor, department, and transcript. And then, and each of these tables has their own primary key. So, index covering, as I told, index covering means that index is covering some part of the search facilitated, okay? If all of the attributes, okay, of a query, a search query, all of the attributes that we are searching, using the search, included in the search key of a dense B+3 index, then the search can be, the result can be computed only by using that index. Why? Suppose that you have a Suppose that you have a B+3, the search key is based on name of the person, last name, and let's say the student ID, like not a student ID, let's say birthday. Okay, this is the multiple value search key for this B+3. So if you have a range query on all of this, for example, if you are searching for Andy Roberts, or Andy who the last name is less than Anderson and Roberts. So if you are doing the search on just in these 2 items, how do you complete the search? You start on the rooted tree, you go down, you look for Andy, you find the first Andy, okay? Then you go on, the leaves are sorted based on the last name and the birthday, right? You go and find, and you start traversing the linked list, finding Mr. Anderson, if Anderson is existing, or some record greater than Anderson, and then going through until you find some person greater than and equal to Roberts. All of the records found. So you can process the query only and only with the index. So the result set can be computed from the index alone. Okay. Why? Because the search key name and last name was a subset of index, attributes of index. So suppose that the attributes are, there are some attributes in the search that are forming a prefix of the index. So what does it mean? You remember B+3? In the B+3, if the B+, suppose that I have a B+3, the search key is these attributes. Okay? If I look for Mr. Anderson, who was born in January 1st, 1970, can I use this index or not? Can I start from the last name and search? No, because the
order of the search key is from name, last name, and birthday. Now, the leaves, the recording, the leaves are not sorted based on the last name and birthday. They are first sorted based on name and then last name. Because, for example, you may have Michael Anderson, a lot of name happen, like, let's say, who is after Michael? Reza. Reza Baseda. Obviously, Baseda is that's okay. Reza Zakiri, let's say. Okay, so obviously, Anderson is not a good name. Let's say. Okay, so instead of Anderson, we are looking for someone like Moin. Okay, Michael Moini, like, so, we, for example, we have a Michael Moini over here, then Reza Baseda. The sort is correct, right? Because Michael is less than Reza, right? But you see that the last name is not sorted, because when you are sorting base, first base and that first name, then you cannot go through. So suppose, like a very tangible example, your phone book. If you write your phone book based on the last name, okay, and you are looking for my phone number, and you know that my first name is Reza, you don't know my last name. What do? Can you find my name? No. You have to go to all of the last names, and although even though you sort each last name based on the first name, okay, but you cannot use it again. So now then, when the attributes of the search, when the attributes in the where clause just form a prefix, it means that it should be prefixed. Should be prefixed at least, like name and last name, or name, or something like that. It cannot start from last name or be where say, okay? If they are forming a prefix of search key, then they can be, the index can cover some part of the search. So what we are doing is we are descending from we are traversing the tree from the root, and scan segment. I'll talk 5 minutes, and then after that we'll go. Okay. So if in the matching case, if the where clause included the attributes in the where clause include the prefix of the search key, we can use it. For example, here, suppose that in the professor table, we have this dense index based on the department ID and name, and we have this query. Okay. Now the query, the where clause, which attribute was used in the where clause? Is it the prefix of the key? Yes. So it can cover the search. Okay. It can cover the query. Okay, so non-matching cases. So in cases that we have the index but we cannot use it. If the attributes in the where clause do not include a prefix, then we have to scan entire leaf level. Okay? We cannot use this part of the tree. We have to start from the beginning of the leaves and go through all of the leaves. For example, here, if we have an index, dense index, based on ID, name, address, and we are looking for a student ID and a student name where the address is 1 Lake Street. Can we use this? No, because latest address is at the tail of the index search key. It's not the prefix. So
So this index is not useful. And it doesn't cover. So, okay, now we want to talk about how to choose index. So let's put choosing an indexes for the next class. I'll continue on this in the next class.